Hello everyone. We are still introducing probability. In this particular video, we will discuss the operations that can take place on events. First, we'll introduce the concept of complement of an event. In terms of notation, if A is an event, its complement will be denoted by A bar. A bar is the event that occurs whenever A does not. In other words, they are opposite events. In a Venn diagram, we can draw event A and represent it by a set that is contained in the sample space. A bar, its complement, would be all of the events that take place outside of A. The probability of a complement is obtained in the following way. We can find the cardinality of A bar and divide by the cardinality of the sample space. This is also obtainable by eliminating from the sample space all events or the cardinality of event A. In other words, if A is not occurring, then A bar is occurring. Again, they're complementary. Now, if we divide term by term, we'll notice that what we end with is 1 minus P of A. This makes perfect sense. Obviously, if event A has a 30% chance of occurring, then it also has a 70% chance of not occurring. So they are complementary probabilities. So this is a formula to keep in mind. P of A bar is always obtained from 1 minus P of A. For example, if two regular dice are tossed and their respective outcomes are noted, then the sample space consists of the following outcomes: 1, 1, 1, 2, 1, 3, and so forth until 6, 4, 6, 5, and 6, 6. If we consider the event A as being obtaining a sum of 6, then in listed form, A is observed with the combinations 1, 5, 2, 4, 3, 3, 4, 2, and 5, 1. The complement of A would then represent the event obtaining a sum that differs from 6. So, A bar would consist of all sample points in omega, excluding those that are in A. The size or the cardinality of the sample space is 36. The cardinality of event A is 5. So the probability of A being observed is 5 over 36. Now the complement event, obtaining a sum that differs from 6, would therefore be 1 minus 5 over 36, which is 31 over 36. Intersection of events. So if A and B are events, then their intersection is denoted by P of A intersection with B. So the upside down U is the symbol for intersection. The intersection of A and B is the event that occurs when both A and B are observed. In a Venn diagram, you can visualize A and B as being individual events that are contained in the sample space. The intersection of A with B is the area that is contained at the intersection of the two events, so where they overlap. The probability that A and B will be observed means counting the number or the cardinality of the intersection of A with B and dividing by the cardinality of the sample space. So this means we'll have to be able to count how many elements are in A as well as in B. For instance, if two regular dice are tossed and their respective outcomes are noted, then event A could be observed, which is to obtain a sum of 6. Here is the listed form for A, and let's suppose B is that the dice show the same number, whose listed form would consist of the 6 sample points, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. The intersection of A with B must be filled with elements that are both in A and in B, and that is restricted to the combination 3, 3 in this case. 3, 3 produces a sum of 6, and 3, 3 are dice that have shown the same number. So the probability of the intersection of A with B is 1 over 36, since only one element, only one sample point, realizes both A and B. Certain special cases, when A and B are disjoint or mutually exclusive, this means that A and B's intersection is formed of an empty space. There is nothing at the intersection. And the probability that A and B will occur together, so the probability of the intersection, is 0. If A is included in B, then the intersection of A with B is equal to A. That's where B and A overlap. And therefore the probability of the intersection of A with B is also the probability of A. The union of events. Now, if A and B are events, their union is denoted by AUB. So the U symbol stands for union. The union of A with B is the event that occurs when A or B or both of the events occur. So in a Venn diagram, again starting with A and B as being events contained in the sample space, we have the union of A with B, which consists of all sample points that are in A, in B, or in their intersection. The probability of the union. Okay, well, as before, to find the probability of A's union with B, we'd have to find the cardinality of A union B divided by the cardinality of omega. But we could also think of the probability of the union as being the probability of A added to the probability of B, from which is subtracted the probability of the intersection. It's probably better for us to visualize this relationship in order to explain it. So here we have our events. The probability of A is highlighted in yellow. The probability of B is highlighted in blue. And you probably notice when we highlight these two regions, we have counted the intersection twice. So we have to remove the intersection from our calculations. Two regular dice are tossed and their respective outcomes are noted. Using the same events as we had previously, let's suppose A is that we've obtained a sum of 6 and 5 sample points fulfill event A. Event B, the same number appears on both dice, so 6 sample points make B true. The union of A with B would be the list of all elements that are found in A or in B or in both. So although 3, 3 does appear in both lists of A and B, of course we only write it once in the union. The probability of the union is obtained by counting the number of elements in the union itself, and there are 10 elements, divided by the size of the sample space, which is 36. Notice how the same outcome is obtained by using the second rule that we wrote. So P of A is 5 over 36, P of B is 6 over 36, and in A and in B we double counted the sample point 3, 3, so we're subtracting 1 out of 36. And in the end, 10 over 36 is our probability of A's union with B. Special cases, if A and B are disjoint or mutually exclusive, then the probability of the union of A with B is restricted to adding P of A and P of B. This time there's no intersection to subtract from this addition. If A is included in B, then the union, formed of all elements that are in one or the other or in both, would reduce to B entirely. And therefore P of A union B would equal P of B. Of course, all these operations can be combined. So, for instance, in a Venn diagram, we would display the event A's complement intersecting with B as follows. So, in the first place, here is a drawing to show the complement of A. Notice how everything but A has been highlighted. Here is event B. Now, the question here is, what do we get when we intersect A bar with B? So when we intersect, we have to think of where did the blue and the yellow mesh to create green, because we want all the events or all the sample points that matched with both. And we see that the outcome of this intersection is what we find in B, but not in A. So using the Venn diagram, we can then calculate the probability. The probability of A complement intersecting with B occurring is what's left when we start off with P of B and remove the intersection out of A with B itself. So Venn diagrams are very useful to break down probabilities into simpler parts. In a Venn diagram, what would the graph of A's complement intersecting with B's complement look like? So again, if we look piece by piece, here is the complement of A, here is the complement of B, and we are looking for the intersection of complement of A and complement of B. So if we match them together, again, the green regions, I'll go backwards here. Yeah, so notice how all the regions that have blue and yellow at the same time then become green when we combine them together. Those are the intersections because elements are part of A bar and of B bar. So this would essentially be everything outside of A as well as B. Or, if you prefer, it's the complement of A's union with B. Again, using the diagram, we can compute the probability of A's intersection with B. Perhaps the better way is to use what we observed, which is that this event is also the complement of A union B, and then we can use previous relationships, in this case 1 minus P of A union B. Okay, so in the graph we can see that everything that happens outside of A and B we can find by excluding from 100% or excluding from 1. These are actually called de Moivre's identities. So in our last example, we saw one of these relationships. So de Moivre actually says that the complement of A union B is the intersection of the complements of A and B individually. And likewise, the complement of the intersection of A with B is obtained from the union of the individual complements.